Alright, welcome back. So we were talking about sets, and we were learning how unfortunate it is that we could put sets inside of sets. That makes things very complicated. But we have powered through it, and now we are ready to get to a much simpler topic. So let's talk about union and intersection. So set union looks a whole lot like OR, but we made it curvy again. So set union just joins two sets together into a bigger one. So defined in math, it's this. A union B is all the x's such that x is in A or x is in B. Okay? That's the idea. So A union B, therefore, contains all the elements that are in either A or B, or even in both. So for example, let's have A and B be this. 1, 2, 3, 2, 3, 4. And then B is 2, 3, 4. So that's B. So A union B is just anything that's in either. So it's this whole thing. So all of them together. Okay, so that's A union B. In either A or B or in both. So it's the set, if we write it out, it's the set 1, 2, 3, 4. Okay. On the flip side, if you swap your OR with an AND, you get set intersection. So that extracts the common elements of two sets. So A intersect B is all the x's that are in A and in B at the same time. So A intersects B contains all the elements that are in both A and in B. Okay? So again, if we have A and B being 1, 2, 3, and 2, 3, 4, let me draw these a bit nicer. 2, 3, and there's a 4 there. So there's A, there's B. A intersect B is everything they share in common. Okay? So, boop, it's that thing right there. So this right here is A intersect B. Because 2 is in A and 2 is in B. Same with 3. Okay? So I hope you see the similarity between union and OR and intersection and. They're actually defined using them as well. So that's funny how you just made some things curvy and they kind of take on a new meaning. So that is union and intersection of two sets. Not too bad, I don't think. So let's test you on those to make sure they're making sense. So here are your three sets, A, B, and C. Go ahead and figure out what A union B, A intersect B, and A union B intersect C first is. Okay, let's do it together. So A union B is just all the stuff that's in A or in B, so everything. Just write them all out. So there's a 1 because there's a 1 in A. There's a 2 because there's a 2 in A. There's a 3 because there's a 3 in A and a 3 in B. So I hope you see where I'm going with this. Then a 4, then a 5. So it's all this. Yeah? A intersect B now. What do they share in common? Bam. They share a 3. And that's about it. So it's just the set containing 3, and I accidentally wrote a closing brace. There we go. All right, what about A union B intersect C? So you have to do B intersect C first, because those are in parentheses, and then you can union with A. All right, so let's do B intersect C first. What is that? Well, that's the set of all the things that B and C share in common. So it looks like they have a 4 in common and nothing else, right? So we got 4. And then A union, this is just all the stuff in A with the 4 as well, if the 4 wasn't already in A. So it's just 1, 2, 3, and 4. Because you take the 1, 2, 3 from A, and then you can take the 4 from B intersect C. You see that? So hopefully this is all making sense. And these are the answers, and I hope you got them too. Okay, sometimes we have more than just two sets. Union and intersect, they're supposed to be binary operations, but you can make them work for sequences of sets at a time, which is fun sometimes, and sometimes it's also useful. So, yeah, we want to take intersections or unions of a bunch of sets at once, and we don't like having to write, okay, A1, union, A2, union, dot, 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 union, A to the n, AN. So we made some notation that looks a whole lot like some notation summation notation. And it looks like this. We take the union, start I at 1, go to n of a of I. Okay, so that is equivalent to this. So that's just, okay, set I first being 1, then, okay, it's a to the 1, a1 union, a2, a3, because I is ranging between 1 and n. Okay, hopefully that makes sense. And this notation is not too hard, considering that you know about probably summation notation. Okay, so that is all the unions of a certain sequence of sets. And so yeah, this is like a for loop. You start I at 1, and then you increase it until it's equal to n. And you're going to union each AI together as you go. So hopefully that's all coming to you. And the same thing works for intersections. So again, you maybe have seen sigmas work like this before, but we're doing it for unions, for intersections now. So if you just flop the union for an intersection, this is all the same. It's start I at 1, go to n, intersect all the AIs. Okay? So a1, intersect a2, intersect an. Okay? And that's the name of the game. And that's what you do. So that's unions and intersections of sequences of sets. And let's have some practice with that now that we've defined it. Let's make sure we understand it. So let AI be this set, I to the I. And it depends on the I, remember. Okay, so the I is affecting these things. So for example, A7 is what? Well, if the I is 7, that means that's 7 and 2 to the I, which is 14. Or 2 times I is 14. See that? So what is, from I, the union of all the AIs from I starting at 1 going to 3? Okay, so let us work on that. And actually, you try it first, and then we'll do it together. Okay, so let's write it all out. So this is equivalent to, it's equal to A1 union A2, just following the definition, union A3. Okay, and now what's A1? Well, that is 1, 2 times 1. Yeah. 1, 2. Union. What's 2? Well, it's 2, and then 2 times 2, 4. Union. 3. Well, that's 3. 2 times 3 is 6. Okay, you see how these AIs are coming out of this? And then what is this? What's the union of all of them? Well, it's 1, 2, 4. There's a 3. I guess I can put it first. 2, 3, 4, and 6. Okay? So it's missing a 5. That's the idea, because it's prime. Okay, so hopefully that is making some sense. You just follow the definition, really, and it'll all work out. Okay, so that is unions and intersections of sequences of things. And there are actually some more operations on sets that you could have. There's the difference and the complement. So these are very useful. So the difference is using this minus symbol. And what it is all the values that are in A but not in B. Okay, so the order really does matter. So A minus B is just all the stuff in A but not in B. For example, let's take A being 1, 2, 3 and B being 2, 3, 4. What's A minus B? So here's A, 1, 2, 3. Here's B, 2, 3, 4 as usual. A minus B is all the stuff in A but not in B. So here's all the stuff. It's right here. I think you see it. All the stuff in A but not in B. Right there. That's A minus B. It's just the 1. Just the set containing 1. Because 2 and 3 are in B. And so they get subtracted out. Gotcha? Okay. And now we can finally come back to this idea of the universal set. So once you specify it, or it's defined in context, what you can do is you can negate a set by creating its complement. So for example, let's see here. Let's define it first, and then I'll give an example. So the complement of a set A is just a bar with a bar on top. It's essentially the negation. It's essentially the negation in set form. Kind of. You can think of it like that. It's like not A in a sense. It's all the things in the universe that aren't in A. So let's take everything but the stuff in A, really. Okay, so alternately defined, A bar is the universe minus A. Okay, you see how that's the same as this? It's all the stuff that's in U, but not in A. Okay, so for example now, let's let A be the set of all the positive integers that are greater than 10. Okay, so that means A is equal to 11, 12, 13, and so on. And let's say that the universal set for this example is Z+, so the positive integers, remember? What is A bar? Well, let's spell this out for a second. That's 1, 2, 3, ... What is A bar? Well, it's all the stuff in the universal set minus A. That's not in A. All the stuff that's not in A that are in our universe of discourse. So that's all the stuff before 11. You see how it's going to, like, this is all going to wrap around once you hit 11, and it'll just keep on being excluded. But all the stuff before 11, well, that's only in Z+. It's all the stuff that's only in the universe but not in A. So the answer is A bar equals 1, 2, 3, all the way to what? 10. Dun, dun, dun. Because 10 is it's the last thing that's not in A, but is in Z+. Okay, so this is a lot of symbol pushing. It's a lot of thinking hard about things, but hopefully it's all coming to you. Please yell at me in office hours or on Discord if any of this is not making sense. I actually installed a Discord bot specifically for typing math notation, and I am excited to show it to you the first time I get a question on it, on this kind of stuff. Okay, so that is difference and complement. And now, notice that I've been doing this. I've been defining all these operations in terms of logic. And is a logical operator. Technically, element of is something that can give back true or false. It's a logical operator on sets. We can now have identities, just like we had logical identities. We can have set identities. Okay. So, and the reason we can do this is because set operations are defined using logic. The set identities actually look very, very similar to what you already know. So here's a list of them, and bam, if you just replace ors with unions and ands with intersections, and true with the universe and false with the empty set, oh man, this is all very nice. This is all making sense. And like knots with negation, it's all the same. It really is. So this is fun, and this is useful for us as mathematicians who are about to define the rest of this class in sets. Okay, so let us show the first De Morgan law. This one, A union B complement is equal to A complement intersect B complement. So it's like union flops with intersection, just like or flopped with and so it's where is it? There it is. It's that one right there. And of course you have the opposite one as well. So let's prove that. Let us prove this together. And here's the secret. So your book likes to prove these equivalences in terms of, okay, let's just take an arbitrary element and let's see if it's in this thing. Let's prove that it's also in this thing. Okay, that's how you make sure that these two sets are equivalent if something that is in this is also in this. Okay, so let's start on this side. Let's say, okay, we have some x, and we know that it is in A union B complement. So now we can unfold this because all the definitions that I've been giving you, they're equalities, so they're bidirectional. And so if and only if this is true, then it's also true that x is not in A. Okay? So we can just unfold all those definitions and get this. Now, x is not in, that's an in, A union B. Okay? So I took away this complement by using the definition of complement, I added a negation, and then took the inside. Okay, and this is the trick you play, because the definition of union now is this. this is the not, we'll carry along. Okay, it's a union if X is in A or X is in B. You see that? Hey, hey. So, are you ready now? We can now use normal De Morgan's law on logical things. So this is saying, okay, negate this, negate that, flop this to an and. This is going to be useful. Okay, that's if and only if X. It's not true that X is in A, and it's not true that X is in B. So we can now unfold the definition of intersection. Let's see here. Or you know what? I think we first need to do the complements. So this is if and only if X is in A bar, because it's not in A. X better be in A bar, and X better be in B bar, because it's not in B. Yeah? Alternatively, you can write not X in blah A as X not in A like that. Those both work. So now we have this, and now we can use the definition of intersection, which involved an and. Okay, so that means if and only if X was in A bar intersect B bar. And that was exactly what we wanted to get to. Okay, so we started here, picked an arbitrary element out of this, A union B, and then we saw that it was also in A bar union, A bar intersect B bar. So all that is the same as that, and you can go both ways. Like we went from left to right in our proof, but you can go from right to left because these are all biconditionals. Okay, so this is our proof, and this is why it's true. So then you can just go straight to saying, okay, therefore, the sets must be equal, because every element that is in this one must be in this one, and vice versa. Therefore, A union B bar is equal to A bar intersect B bar, and that proves the first De Morgan's law for sets. And yeah, hopefully this is all making some sense. This is all the same as logic. It's really not too bad, I think. And yeah, fun stuff. So now I want you to try it. So go ahead and use set identities to prove that A intersect B bar, B complement is equal to the empty set. Okay, so name each identity as you use it, as usual, and then we'll come back here and do it together. So you can totally go back to this kind of style in which you're using logic to do all this, but it's a lot easier to just take the identities as face value and use those. So you don't have to get involved like X is in this, blah, blah, blah. So let us start with what we have, A intersect B bar, and so that's what we started with, and then let us move along. So I think you'll see that this is like anding true, anything with its complement is always going to give us back the empty set, because there's nothing in that complement. So we'll use that complement law right there to give us that, and that turns this into A intersect the empty set. So complement law gives us that. That's what we have there. And then, well, anything intersected with the empty set is also empty. And oh man, we have that from the domination laws. And that's like saying anything ANDed with false is still false because of this equivalence. Okay. No, sorry, it's just empty set. And it was the domination law. Okay, so really not bad. Just using all the logical stuff we know and love already to prove these bigger things. Okay, so that is that. And now we are on to bigger and better things. Okay, so we've been talking about individual elements. Technically, you can have sets of sets, but there are also these things called pairs that we like to use where the order really matters. Let me get rid of this grammar error because it's not a grammar error. So we like to write in programming a whole lot A comma B, like we have pairs of things where A is the first thing, B is the second thing, and that order really, really matters. And so we can define pairs in terms of sets because that's our goal, remember. define all of mathematics with sets. So now we're going to secretly do that. One thing at a time. So pairs can be defined as sets this way. This is one way you can do it. Well, we have to figure out which one's the first one, which one's the second one. We can specify it in this way. We can say, okay, the first thing, the pair itself, we can define it to be the set of these two subsets, of these two sets. The set containing A and the set containing A and B. And the one that is by itself is the first thing, and it better be in here too, and this is the second thing. Okay? And the reason you have to do that is because the order really matters. It's because A comma B, it really is the same as B comma A. So this is the only way we had to do this trickery to be able to say that, okay, yeah, the one that's by itself, that's the first thing, because this is exactly the same as B comma A. We wouldn't have known otherwise. So that's the silly definition, and now we can just use this and assume that we can define it if we ever needed to. Okay, so that's a ordered pair. A comes first, B comes second. We can get down to the set level and define it if we would like. Okay, so let us move on now. Where do these pairs come from? How are we going to define them formally? They come from a Cartesian product set, okay? So we say that the Cartesian product, and this comes from Descartes, the Cartesian product of two sets A and B, it's the set of all the ordered pairs where the first entry was from A and the second entry was from B. So we write that as A cross B. That is the Cartesian product of the sets A and B. So let me break it down for you very, very slowly. If A is 1, 2, and B is ABC, what is A cross B? And it bothers me that I fixed this cross but not the others. It's not an X. It's a different thing. It looks better that way. Okay, so it's just every pair. A cross B is every pair where the first element is in A and the second element is in B. All the ordered pairs, first entry is in A and the second entry is in B. Okay, so A is 1, 2. So I can make this pair 1, comma, and then something. So I took something from A, let me take something from B now. I'll take an A. So there's one thing. I could alternatively have taken the B, the pair 1, comma, C. So that's all the things with 1 and something else from B. And then we can do the 2's now. So 2 is the first element, and then A can be the second element. So this is a nice little ordering that I have, but obviously it's a set, so the order doesn't really matter. 2B, 2C. This is the set of all, dun dun dun, the set of all ordered pairs. One thing from A, the other thing from B. And we'll come back to this in a second. This is a funny thing. Okay, yeah, let's talk about the size first of all. If you have A cross B, how can you do a little sanity check and make sure that you put everything in there? Well, you can see that you're taking one thing from A, and there's 2 things, and one thing from B, and there's 3 things. That should naturally prove to you that the size of A cross B, well, it's just the size of A times the size of B. Because you got to pick one thing from here and one thing from here, and you can choose all the different pairs. Okay, so it's like a for loop in a sense. You're choosing all the possibilities. Yeah, so that's A cross B, and that's the size of A cross B. It's the same as A times B. 2 times 3 is 6. There's 6 elements here. That's ordered pairs, and so this is not the same. Remember that 1 comma A is not equal to A comma 1. That is a very different thing. This is now ordered pair land and not set land. Okay, so that is what I wanted to show you there. Those are ordered pairs. And let's actually put this on the next slide for fun. So you can cross together, though, more than just 2 sets, just like you can intersect together more than 2 sets, union together more than 2 sets. And then you can just start making triples and quadruples and things like that. So an ordered triple looks like this. A is the first thing, B is the second thing, C is the third thing. The order matters. And they come from Cartesian products of 3 sets. So like you took the A from the set A, the B from the set B, the C from the set C. And then you can do this as long as you want, like A times D times E times F, up to n sets at a time, and you make things called n tuples. Okay? So those are elements of Cartesian products for greater than 3 sets. I guess you could say quadruples. 2 also works, so let's just say that. So pairs, it doesn't really matter. So here's the idea. This is a valid quadruple. It's a 4-tuple, where you took the first thing from this set, the second thing from this set, the third thing from this set, and the fourth thing from that set. Okay? Because there's the 2, there's the A, there's the B, and there's the 7. Yeah? So that is an n-tuple. And you can also write this, if parentheses and commas are not your thing, using what's known as string notation. So you can just plop them all next to each other, get rid of the commas, get rid of the parentheses, and write 2AB7 instead of 2, A, B, 7 for this. Okay? And a funny thing is that nobody agrees on how to pronounce tuple. This is how I learned, and obviously I'm teaching you that way, but there are multiple. So let's go here. So there are 2 possible pronunciations. One to rhyme with tuple, so tuple, and another with supple, so tuple. People also say tuple in addition to tuple, and people do not agree at all. So you are allowed to say is pronounced, that is an N, tuple, or like, I don't know, tuple. How about that? So tuple or tuple. Pick your poison. I like tuple. All right, so fun stuff. Now let's get some practice. All right, so here are my sets. A is the set just containing A, B is the set containing B and C is the set containing A, B, and D. All right, so I want you to write all the possibilities. What is A cross B union A cross C? Okay, so write it once using the n-tuple notation, and again using string notation. All right, and then we'll get to B after that. So give this a shot, and then we'll come back and do it together. So let's see here. A cross B union A cross C. Let's do this. Let's figure this out. So A cross B, let's figure that out first. A cross B. Well, that's all the pairs where you could take one thing from this, and the first thing from A, and the second thing from B. So that is, do it with me, A, B, comma, A, C. Those 2 pairs are the only things you get, because you got only one thing and then 2 things here. So A has to be the first thing, and then B or C could be the second thing. Yeah? That's A cross B, and now A cross C, very similar. That's going to be, well, you only have A to be the first thing, and then you have A, B, and D to be the second thing. A comma A comma B, A comma D. So those are my 2 sets, and if I union them together, I get a third bigger set, usually. A comma A, I'll try and do this in a nice order. A comma B is there, A comma C is there. B is actually shared by both, which is nice to think about. Then we have, A comma D. Right. So we got A comma A, B, C, and D. And B is a duplicate. All right, so that's Cartesian products. A cross B union A cross C. All the possibilities of pairs. And now try this one. What's B squared? Because you can use this notation now. It's just B cross B. Remember that. So B squared is equal to B cross B. And if that didn't make sense before, now try it. What is B cross B? Well, the first thing needs to be an element of B, and the second thing needs to be an element of B. So assuming you've tried it, let's do it together. Dun, dun, dun. So let's pick one thing from B and a second thing from B. So I can pick B and then B again. Why not? Then I could pick B and C, and then I can pick C first, and then for my second thing I could pick B. Or I could also pick C first, and then for my second thing, not A, sorry, then I can pick C. You see how we have 4 possibilities again, because B's size is 2. The size of B cross B needs to be the same as the size of B times the size of B. It makes sense. It has to be of size 4, and these are the 4 things. That's a nice sanity check for us. Okay, so hopefully you got that. Those are Cartesian products, and let's do it one more time. Let us let us prove that these two sets are equal using the stuff that we already know about intersections and unions and things, but also, here's the definition of Cartesian products. X comma y is in A cross B if and only if the first thing was in A and the second thing was in B. Woohoo! Okay, so let's do it how we did it the first time. Up here, we took a random element, and we're like, okay, we're going to prove that if it's in this first thing, it's also in this second thing. All right, so that's the name of the game. And so give this a try, and we'll do it together. Okay, so let's say that we have an X in A cross B intersect C, and we want to eventually get down to knowing that A must have been in this as well. Okay, and it's if and only if, so we can go backwards as well, and that was exactly what we needed. Okay, so let's do this. Let's unravel this somehow. How can we do it? Well, we can definitely use Cartesian product right now, probably, because if, let's see here, if X is in this, well, maybe we should say X comma Y, actually. That would make more sense. Instead of just one big thing, let's make it a tuple, a pair. So X comma Y is in A cross B intersect C, if and only if, well, the X must have been in the A, and the Y must have been in B intersect C. Yeah, that's not too bad. So that's exactly what we want so far. And now we can break this up as well into some pieces. Okay, so how can we do that? We can say that, well, X is in A, that stays, and, well, if something's in the intersection, that means it must be in both. So Y is in B and Y is in C. And I could use the parentheses, but you know by the associative rule that those can just go away. Okay, so now I know this. I know all of this. And now I need to start making it somehow to look like this. One thing that I'm going to do, which maybe doesn't make a whole lot of sense right now, but it's what you need, you can just bring in something else. You can use these idempotent laws for logic, for ors and ands as well, if you remember them. So I can just say, okay, yeah, this is all the same as X is in A, and Y is in B, and X is in A again. That doesn't ruin anything. It's there twice. It's fine. And Y is in C. And then I can use my associative law. So I'm just going to do all these together. To do that, oops, let's make these prettier. And then I can use my definition of Cartesian product again in the reverse direction. I can go that way now. Bam. So, are you ready? So this is saying that X is in A cross B, and, oh sorry, XY is in A cross B. Let's say that. X comma Y is in A cross B. So I'm using this with the definition of Cartesian product because I have this, and I'm going to make this out of it. And I have that X comma Y is in A cross C, okay? Because now I'm using this, because I have these two things, and now I'm making this thing. Are you ready? And now, finally, oops, this is in both directions, of course. And this is all true, if and only if. Now we can finally go backwards with the intersection rule, okay? I can bring this along, because I have this side, and I can use the intersection now. So, therefore, X comma Y is in A cross B intersect. This is an in, sorry, A cross C. Okay, I hope you see my logic, and here's how it's working. We started with something here, and we proved that that same thing was also there. And we went this way, but you can also go backwards, because these are all ifs and only ifs, which can go either direction. Okay, so therefore, this is all you need to show, that A cross B intersect C, it's like a distributive law, is equal to A cross B intersect A cross C. So you could use either one if you needed to. Maybe one's better for your purpose. Okay, so that is a lot of stuff involving Cartesian products. And let's see, I think we have enough time for strings, so let's go through those. All right, so a string is something you know very well, right? That's a type in C++. Shouldn't be too bad. We can define strings mathematically now to be a bunch of characters. And how can we put a bunch of characters in order but by using n tuples? Ho ho! Isn't that fun? So you can have strings in a certain of a certain length, of a length n, built up using a certain alphabet. We call that alphabet A. So that's the set of all the characters. Okay, so that's the set of characters. Set of chars you can use to make your string. Okay, so for example, if my alphabet is this set of A through Z, then using string notation, hi mom is in A5. Okay, A to the power of 5, because this is H, comma I, comma M, comma O, comma M. Okay, and that is in string notation this, and that is 5 things. So A cross A cross A cross A cross A. Yeah, so that is a very nice example of a string, and it's all coming together now. This is a string of length 5, so you can take the length of a string, and this means that strings are also secretly sets. You see what we're doing here? We really are defining all of mathematics with sets. It is the truth, and you're finally starting to see this all unfold. Okay, so this A, B, C, D in string notation, that's really the tuple A, B, C, D, which is really in set notation, if you unwind that definition a bunch of times, that weird looking set. And so it's all building on top of itself. It's all so cool. Now I think you're starting to see the light. I'm sorry, it took us 28 slides to get there, but you're starting to see the light and the purpose of set theory. This entire chapter is just a bunch of definitions, but we're eventually going to start defining more things in terms of sets and talking about things at a higher level, because now we have set theory under our belt. Okay? So that's the beauty of it all. And let's talk about strings a little bit more, and that'll be that. So we can have binary strings, and that's just any string whose alphabet is 0, 1. So the set 0, 1, so like, I don't know, this is 1, 0, 1, 0, 1, 0. That's a string in 0, 1 to the power of 1, 2, 3, 4, 5, 6. 1 to the 6. So it's just a string. It's a binary string. Over, so yeah, a binary string is just any string over the alphabet 0, 1. Gotcha. And every alphabet, or every string, you can also have a concept of like the empty set, the empty string. Okay, so there is a unique string we define whose length is 0. Okay, so we use the Greek lambda for that, and usually it's lambda, sometimes it's epsilon, but we're going to use lambda in this class. And I think that lambda probably comes from the German Leer, because, I think I just pronounced that as in Spanish, sorry, but they also have this word, and that means empty or blank. And so they like to use the first letter of things, and they just convert it to Greek because they ran out of Roman letters for no good reason. So that's why we use lambda for that. And so, for example, something like, I don't know, hi mom, I can put a lambda anywhere and it's just all the same. Okay, that's the idea. And that putting stuff in places is called concatenation. So you can, like, you know how in C++ you can say like ABC plus DEF, that gives you back ABC DEF. This process is called concatenation. Okay, that's the formal way of saying it. So if you put two strings together, ST, go away, error, that's correct. So you just put them right next to each other, and that's called the concatenation of two strings. So that was the first string, and then the second string, one after the other. You see that? So S and T, S concatenated with T looks like this, and it's written like that. And so if you're going to concatenate lambda anywhere, because it's the empty string, it doesn't really do anything. You can concatenate it at the beginning, somewhere in the middle, at the end. That's all just the same string because it doesn't do anything. So it's like, hi mom, concatenated with lambda anywhere, with as many as you want, actually. Let me do that. M, lambda, O, lambda, M, lambda. That's the same. That's the same as hi mom. Okay, so that is that's strings in a nutshell. And we are essentially done with sets. I would like to stop here just to let your brain rest, but we just have a few slides after this, and that'll be that. But you are almost all finished. So I know that was just a lot of new stuff. This is a weird chapter. It's a lot of definitions. It's a lot of using those definitions and applying them. But it will pay off, I can promise, in this class and in future classes that you take, because some things, they make the most sense defined using sets. And if this is math, we're going to define everything with sets. Okay, so that is everything that I want to talk about this week. Thank you for bearing with me. I know this is a weird chapter, but we're almost there. And so I will see you next week.